Okay, so we'll jump right back in where we left off yesterday. So we were discussing the current leading Neutrinoless double beta decay sensitivities and limits. And I'm being very choosy here, right? So I'm looking for things that have a half-life limit of over 10 to the 25 years. But there are a lot of detector technologies that have been proposed for Neutrinoless double beta decay searches. And just because I'm not talking about them today doesn't mean that they're not interesting or potentially useful. But these have been the experiments that have gotten here first. And they are also related to the technologies that are best poised to scale up to the ton scale in the near future. So that's why I'm going to emphasize these. And I know you heard a little bit about these already, but I'm going to keep going. And just notice that as we interpret these limits through the lens of our imperfect knowledge of nuclear matrix elements, we are in the about 100 millielectron volt scale in terms of our limits on the neutrino mass. The best one down here for the most favorable xenon 136 nuclear matrix elements is 36 millielectron volts. Right? But we don't actually know those nuclear matrix elements, so we really need to take that whole range seriously. And we also need to take seriously the fact that there may be, we may be off in our nuclear matrix element calculations. So we're going to keep going. Last time we talked about Gerda and how it had effectively ruled out, and also Majorana demonstrator had effectively ruled out the claim for Neutrinoless double beta decay observation in the Heidelberg-Moscow experiment. But germanium is such an attractive technology that they're continuing on with it. So Gerda and Majorana demonstrator have joined forces. They formed the Legend collaboration, and they're currently operating a detector called Legend 200 at the Gran Sasso National Lab in Italy. And as you can see, this is a picture of part of the payload for Legend 200. And it's an assembly of all different shapes and kinds of detectors. So these are all enriched germanium detectors. So they're all operated as germanium diodes. But they've been recycled, basically. We've taken some detectors from Gerda, we've taken some detectors from Majorana demonstrator, we've refurbished detectors, enriched detectors from previous experiments, and we put them all together just to maximize the amount of mass that's in our payload. And so we see those germanium detectors. We also see the instrumentation, these wavelength shifting fibers that form the readout for the liquid argon veto, and then the whole thing goes inside a water tank for a further veto and shielding. And so there's currently 142 kilograms of these high purity germanium diode detectors installed at Gran Sasso. 130 kilograms are operational, so not all of the detectors worked when they cooled down. And the preliminary background index that they've measured is compatible with their background goal, so 2 times 10 to the minus 4 counts per keV per kilogram per year. And one of the things that Gerda, Majorana demonstrator, and Legend have that Heidelberg-Moscow didn't have, remember one of the problems was we couldn't tell the difference between that peak coming from Neutrinoless double beta decay or from a very weak gamma transition, right? But these detectors actually have pulse shape discrimination. And so these have a special point contact configuration. And so when we drift, we can actually see based on the timing of the signal whether all of the energy was deposited locally, like what happened in a double beta decay. So those betas aren't going to make it very far. They'll stop within a couple millimeters, and we'll get a single energy deposition. Or a gamma ray that's going to be more likely to scatter multiple times in the detector. And in that case, we see those multiple scatters here. And that just comes from the way that the electric field is set up to collect charge in this diode configuration. And so this pulse shape discrimination gives an additional handle that lets us discriminate between double beta decays. Can't really tell the difference between beta decays and double beta decays, but that's okay. And multiple scatters like gamma rays. So it's one additional handle, and after the PSD cut, you can see that it knocks that gamma background right down. There's one extra feature in the spectrum. So this is from a thorium calibration run. So this is the thallium-208 transition at 2.6 MeV. And this has a single escape peak here. So there's also going to be this is when pair production happens and you have two 511 gamma rays produced when the positron annihilates. One of those 511s escapes from the detector, but this still looks like a gamma ray. This still gets knocked down. You can also have a double escape peak. So here's our double escape peak, zoomed in here, zoom in on it. And the double escape peak, both of the gamma rays have escaped from the detector. And so this should look like betas. We only see the betas. And we see that, in fact, the pulse shape discrimination keeps those, right? So this is working very nicely to keep signal-like things and reject background-like things. So if Heidelberg Moscow had this, they would have been able to say a lot more about their peak. Ultimately, the goal of Legend 200 will do a physics search. It's just very early days. They just started running. But ultimately, the goal is to scale up to Legend 1000. And the nice thing about this technology is they can keep adding mass as they get more detectors. For this one, they're actually going to build a new water tank. Legend 200 is operating in the Gerda water tank. But they're going to have a new water tank for Legend 1000. And they're going to operate in a way that lets them have this larger payload. And so they're going to have a ton of enriched germanium diode detectors. And in 10 years of data taking, they're going to reach a half-life sensitivity of 10 to the 28 years. That's really the target for the ton scale. 10 to the 28 years is where we're headed next. Right now we're at 10 to the 25, 10 to the 26 years. So we're going a factor of 100 more in half-life sensitivity. Okay, we've still got that square root to turn it into a mass sensitivity. And the energy resolution here, again, is really the power of these detectors. Their energy resolution goal is 2.5 keV, so something like 0.1% at their Q value. They do require very stringent background reduction, including relevant to a Legend 200. So they have to go even lower in background than Legend 200 is. They do that by using larger detectors. So all of these will be new. They're not all recycled again, right? They're going to use new detectors with a larger volumes. They'll have a better signal to volume to surface ratio. They're going to have better electronics, lower mass, which means lower background. They are going to switch to argon-42 reduced argon. So this is underground argon. It's extracted from underground, so you don't get this cosmogenically produced argon-42. This is also being produced for the DarkSide 20K dark matter experiment. And so this is a collaboration with DarkSide 20K, essentially being able to get this underground argon. And this one's not true anymore. They actually are going to be sited at Gran Sasso. That decision has been made. And that's just going to accelerate their schedule a lot. That's why that's advantageous. So here's the simulation. So if we look at what their discovery potential is going to be, this is a neutrinoless double beta decay signal at that 10 to the 28 year half-life, and the signal is this red blob here. We see that our 2 neutrino double beta decay, as usual, is the biggest thing in our spectrum. And that neutrinoless double beta decay peak does really stand out above the background, although we do have to be careful. There's no statistics here, right? And this is still very, very few counts per keV per kilogram year, right? So statistics is still going to play a role. Even if the neutrinoless double beta decay half-life is in reach, when we do this experiment, we have small number statistics, we still might not see it, right? So the statistics here will be really, really important. But here are their projected sensitivity reaches. So here's the band corresponding to the 10 millielectron volt range in the mass parameter, which is at that 10 to the 28 years. That's where we're aiming for, the bottom of the inverted hierarchy. And you can see if we had a background-free experiment, it would grow like this. The more they're able to reduce their background, the closer they get to this line. But in 10 years, they are going to reach that 10 to the 28 year half-life sensitivity if they're able to get their backgrounds low enough. And here you really see, we've got some pulse shape discrimination, but it's limited by the size of the detectors. Remember, the multiple scattering works better if the detector is bigger. And really, the energy resolution is essential in this case, right? That's a huge part of how they keep their backgrounds low. Here's another solid state detector. So this is the leading result in tellurium, 2.2 times 10 to the 25 years, a 90% confidence level. So Quarry is this bolometric detector. These are tellurium dioxide crystals. They're 5 by 5 by 5 centimeters cubed, and they go into the payload of a dilution refrigerator, cooled down to less than 10 millikelvin. Some of the original articles about this call this the coldest cubic meter in the universe. So it's fun to think about. This is a pretty large, pretty cold dilution refrigerator. And it's built out of low background materials. They also have internal lead shielding. Some of that's built from that same Roman lead that you heard about last week that has low radioactive contamination. And here's what their spectrum looks like. And you're going to see it looks really different from what Majorana saw, right? So here, here's their Neutrinoless double beta decay region of interest. If we zoom in on it, we can see where the peak would be. And we can see that there's nothing there, right? So that's why they're able to set this nice limit. They have a background index of 1.49 times 10 to the minus 2 counts per keV per kilogram per year. So not as good as Legend. And a lot of what's going on here, even after they make their cuts, is we actually have this tail from these high energy alphas. So unlike a lot of the other experiments where they're worried about gamma rays, this experiment background is dominated by alphas. And that's going to set their course for scaling up to a different kind of detector. So the path forward for the Quarry experiment is not to build a bigger tellurium payload. It is actually to change their absorber material from tellurium dioxide to a totally new crystal. And so the idea is a Quarry upgrade with particle ID so that they can throw away that alpha background, right? They need to be able to discriminate between alphas and betas and gammas. And the way that they do that is by adding a second readout channel. So right now it's a calorimeter. They get a phonon signal. They add in photon detectors, and they use a scintillating bolometer. So this bolometer is going to emit light at low temperature. And by reading out both the phonon signal and the light signal, they can construct this kind of scatter plot. And we see that the alphas lie far away from the beta gamma line here. And so this is just going to let them completely throw away all of those alphas that are currently contaminating their region of interest. And this, we've actually had two separate efforts within the CUPID collaboration, one in selenium-82, one with molybdenum 100. They're planning to move forward with the molybdenum 100. And molybdenum has, we've seen molybdenum already. We've seen NAMO study that, and it has that nice high Q value, so does selenium, of 3 MeV. And so they're going to move forward with these lithium molybdate bolometers enriched in molybdenum 100. And they've got a 7.4 keV energy resolution at their Q value, which is also a little bit higher than, is quite a bit higher than the germanium Q value. So sort of comparable, close to that 0.1% energy resolution. And they've demonstrated that these have very good intrinsic purity. So this is how CUPID is planning to move forward. And the nice thing about CUPID is that they can use the same kind of construction, use the same size of payload, and put it right back in that Quarry cryostat. So the fact that they already have this very nice low background dilution refrigerator that they understand very well, that they're currently planning to actually upgrade for low vibration operation, means that they can just move this detector assembly in. So what we have here is this sort of low mass way of holding these detectors. So you want as little dead material around as possible. So this is a lightweight support system. And you can see the thermal readout. And they'll also have light readout. So they do surround it with this reflecting foil. And they're using their current R&D setup to maximize their light collection. That's going to give them the best possible discrimination power for those alphas. And I didn't show their sensitivity. So their half-life sensitivity is not quite as good as Legend 1000. But because of that higher phase space, Legend's at 2040 keV, this is at 3 MeV, this detector, Cupid, which will be that full array, will be very similar in terms of its M-beta-beta reach. So this is an interesting case where the comparing an M-beta-beta space makes this look much more favorable than if we just compare in the T1 half space, even though we have to trust our nuclear matrix elements to be able to do that. So they really win here by going to one of those higher Q value isotopes of molybdenum 100. So both of those were solid state detectors. And for both of them, what we saw was that they can be built really low background. The crystal growth actually pushes impurities out. So they're naturally low background crystals that are grown. And they also have really good energy resolution, 0.1%. And that's a huge part of their ability to achieve low background. But like we said before, if we had a detector that we could scale up without introducing more dead material nearby, we could use this self-shielding effect to really be able to discriminate gammas, right? To be able to keep our gammas isolated near the edges of our detector, we'd have very clean center region. And also look for those multiple scatters as a way of throwing out those contaminants. So that's what I'm going to talk about next. So we do have examples of these very large detectors where we're taking advantage of existing neutrino detector infrastructure. It's already low background. We're adding a neutrinoless double beta decay isotope and getting this large monolithic volume that takes advantage of self-shielding. So for SNO+, this is of course an upgrade to the SNO detector where they're going to use 3.9 tons of natural tellurium dissolved in the liquid scintillator that they've now upgraded the SNO detector with. So SNO has been running with pure liquid scintillator for a while now. They're still trying to introduce that tellurium, so they haven't actually started their run yet. And we remember that natural tellurium has about 30% tellurium-130 in it, so this will have a large payload of tellurium-130, but it hasn't actually started running yet. So keep your eyes peeled. There will be results coming out from SNO+ in the future. But we do have results from CAMLA Zen, and what we've seen is that these are actually leading in M-beta-beta and T1/2 sensitivity right now. So this is, of course, we've got a balloon suspended in the center of the CAMLAN detector. It's also running with pure liquid scintillator. And dissolved in that pure liquid scintillator inside the balloon is 800 kilograms of 90% enriched xenon. So again, we're taking advantage of the low background and large mass reach. Because xenon is a noble gas, there's really no chemistry to worry about. You can dissolve it into the liquid scintillator without doing a lot of work. And we can get up to 3% solubility by weight. And the downside here, and this also applies to SNO+, is that the energy resolution is not nearly as good as the solid state detectors, right? So you're really relying on using the other ways that you discriminate against background. So 6.7% energy resolution. And you can also discriminate multiple scatters, but only if they're sort of 13.7% centimeters apart. So they have to go quite far for you to be able to see the multiple scatters. So neither their energy resolution nor their position resolution are very good. And if we look at their data, you kind of see the difficulty of this experiment. They measure their backgrounds extremely well. And again, we see that xenon-136 2 neutrino double beta decay standing out as the biggest thing in our cleaned energy spectrum. But here's where the neutrinoless double beta decay peak is. And because of that energy resolution, at this kind of half-life limit, we are seeing exactly the thing we were worried about. The 2 neutrino double beta decay tail and the 0 neutrino double beta decay peak are strongly overlapping. So this really limits the ability to scale up more in CAMLA Zen. At some point, you don't win anymore because of this irreducible background from the 2 neutrino double beta decay. So that's why we don't really hear about adding more xenon to CAMLA Zen unless we upgrade it. So there was a proposal to upgrade to CAMLAN 2 Zen, numbers everywhere. And what that means is they're actually going to upgrade the light collection and the liquid scintillator for increased light. So if they have increased light, they can increase their energy resolution. And if they can get that down to sort of half of this, they can go further. It's not currently planned to go forward, but it's a really nice idea because it's still very easy to do this relative to a lot of the other detectors they have to build from scratch, right? Here you just need to build a balloon and buy more xenon. But in this case, they would also have to upgrade their light collection system and their liquid scintillator. Okay, so now I'm going to tell you about the experiments that I work on. So XO200, actually, it's not a current experiment. It finished in 2018. But in this case, we still have this source equals detector technology. It's a monolithic detector in the sense that we just scale up a single volume of xenon. And this is a liquid xenon TPC. If you're familiar with dark matter detectors, you've probably seen dual phase xenon TPCs, very similar to single phase and double phase and dual phase liquid argon detectors. So I know many of you are familiar with those as well. So same exact principle. This is a single phase liquid xenon TPC. So the dark matter detectors need that dual phase. They need the gas phase for amplification because their signals are so small. They need gain in the gas phase. Because our signal's at 2.5 MeV, we don't need that gain, and we can operate as a simpler single phase detector. We tend to win in double beta decay if your detector is simpler because it means you can build it with lower background. So as we know, we have an ionizing particle deposit energy in our liquid xenon. It ionizes the liquid xenon, creates a cloud of ionization electrons that drift in an electric field to a collection plane. It also creates a scintillation signal, which we can read out with photodetectors. And so this is half of XO200. We actually had two of these TPCs sort of smushed together with a central cathode in the center shared between both of them. And and we were able to fill this detector with a total of 100 kilograms. Well, we had 200 kilograms available, about 175 go into the liquid phase, and we ended up with about 100 kilograms in the fiducial volume. It was enriched to 80% in Xeno-136. And again, you can see this is all made of copper. It's ultra low background. It is operated at the Waste Isolation Pilot Plant, which is a nuclear waste disposal facility built in a salt mine in New Mexico. And I can show you a close-up of the readout plane. Oh, no, I can't. So the readout plane is actually down here. There's a cross wire grid that you can't really see behind the cathode. And then these little circles are the photodetectors. The Teflon around the edges is for light reflection. So we do this for two reasons. One is the same reason that Quarry wants to add a second channel, which is that we get particle discrimination. So in fact, we don't have to worry about alphas at all. Alphas are way off this scale on the scintillation versus ionization scatter plot. So we've deployed a thorium-228 calibration source here. We don't see any alphas in our data set. We see this nice beta-gamma spectrum here. We also notice that xenon does very strong microscopic anti-correlation. So the ionization and scintillation signals are correlated, but we see that if you look closely at a single gamma peak, there is an anti-correlation between the scintillation and ionization energy. That means there's correlated fluctuations in those two channels. And so since we care so much about energy resolution, we want to make sure that we use the best possible energy resolution, which happens when you project onto this rotated axis. You're essentially cutting this ellipse at its narrowest point. So we can see here, if we just looked at the scintillation, we would have a 5% energy resolution. Get this green curve. If we just looked at ionization, we would have 3% energy resolution. That's our blue curve. But when we use our rotated axis and we combine them in exactly the right way, we get the best possible energy resolution, 1.2%. And that can be improved with improved light collection efficiency. That was the limiting factor for this detector. So 1%, not anywhere, still an order of magnitude away from the solid state detectors, but much better than the liquid scintillator detectors. Right? So it's kind of a compromise. we get that scaling up advantage, and we have decent energy resolution, just not amazing energy resolution. We also have better position resolution, which means that we're able to do that same trick of looking at single site events and multiple scatters to distinguish between things that are more likely to be signal-like, although you can still have gamma ray contamination, and things that are more likely to be background-like. And so if we just put these things in the two bins based on how many hits we see in our ionization readout plane, if we look again at thorium calibration data, so this is a gamma ray source, then we see most of the counts in the multi-site spectrum that looks like this, multiple scatters, and we see that that's greatly reduced in the single site spectrum. So, it would be nice if this was reduced more, but that's actually not the important thing. The important thing here is that this ratio ends up being fixed at every energy. And so when we measure this single site to multi-site ratio, we can then use that when we later fit our data. So we don't use this as a cut. We don't throw this away. We really use it to measure our background extremely well. There's other ways that we reject gamma backgrounds. One is that attenuation factor, the fact that we know that most of our gamma backgrounds are coming from the surface, and they're going to scatter multiple times because we have a few attenuation lengths in our xenon vessel, in our liquid xenon. And so we call this the standoff distance, so the distance from the edges of the detector. That's another parameter that goes into our physics fits. We don't just have to use the two-dimensional information from our collection plane, we can also use the timing information to look for single site and multi-site events. So a longer rise time is going to look more like a gamma ray, right? It might have scattered in the z direction along the direction of drift. And we can, a short rise time will look more like a beta. So we put some of that information together into a deep neural network to build a neutrinoless double beta decay discriminator. And it's basically a way of looking at the topology of the events. So we're not putting the standoff distance in here directly. This is really based on the signals that we see, our timing information. And so this roughly correlates with the size of the event. And so we can see this qualified on radium-226 calibration data. So this looks like uranium backgrounds coming from our vessel. So this is a good model of our backgrounds, especially our most important background is actually in the uranium chain. And we can see that that agrees with our discriminator. We can look at it in single site and multi-site. And we also have the 2-neutrino double beta decay signal, which is large in our detector, that we can use to qualify what's signal-like in our detector. We can see what the neutrinoless double beta decay signal behavior will look like, but we just can't test that with data. So we put all of this together into a multi-dimensional fit. We put it in, basically tie everything together with our measured parameters from our from our gamma ray calibrations. And this lets us extract our best possible energy resolution. So we're not just looking at an energy spectrum, and we're not doing a cut to get to a signal-like energy spectrum. We're using all the information so that we have a really precise measurement of our background, which ends up being the important thing if you want to constrain everything. So this is what XO200 data looks like. And so again, we see in gray here, the 2-neutrino double beta decay is the biggest thing in our spectrum. So this is phase 1 and phase 2. We did an upgrade between here and here. So we have a little bit better energy resolution in phase 2. And in phase 1, here's our neutrinoless double beta decay best fit. All right, so the best fit was to a few counts in the neutrinoless double beta decay peak. And we can see here that peak is now well separated from the 2-neutrino double beta decay. So this energy resolution is good enough, better than Kam-Lan-Xen, so it's good enough to give us really good separation between 2-neutrino and 0-neutrino. This best fit, of course, was consistent with our background model, so that's not a discovery. That's going to let us set a limit. And in phase 2, with our better energy resolution, we actually prefer no counts in the neutrinos double beta decay peak. So that's why you don't see it down here. So by combining phase 1 and phase 2, oh, also I should say this is single site data, so this is really where we're looking for our signal. This is the multi-site spectrum that lets us constrain our background. So this is where we're really measuring that gamma ray background very well. So you see this is very wiggly. But this is a really important constraint on what goes into the backgrounds here. You can also see the performance of our discriminator. And so for a total exposure of 234 kilogram years, we had a sensitivity of 5 times 10 to the 25 years, and ultimately ended up with a limit because of this fluctuation in the background that's a little worse than that, 3.5 times 10 to the 25 years. So I tell you all of this because it's important to understand that this detector is kind of a compromise. We do a bunch of things okay, but by combining them, that's kind of the power of the experiment. So it's a little bit more complicated than we just make an energy spectrum with really good energy resolution. I'm just going to point out, we also do other searches than strictly the neutrinoless double beta decay. So you can also look for these Majoron modes. So when we're looking for double beta decay, we can also look for, this is again neutrinoless double beta decay, no neutrinos here, but instead we have the emission of this boson. Or you could even have 2 of those bosons. So these are called Majorons. They were originally invented as Goldstone bosons. And so they can accompany this decay. And because there's an extra invisible particle here, we see a broad energy spectrum, and it can have these different spectral indices. So n equals 5 looks like 2 neutrino double beta decay. So we really don't have any sensitivity to that one. But the other ones have a different spectral index. And so what we're looking for is a component of our broad energy spectrum that would look like one of these other spectral shapes. So this is what our Majoron search looks like. You can see we do it for both single and double Majoron emission with different spectral indices. And we're able to set these kinds of limits. So we didn't see it, but it's another sort of BSM thing that's fun to look for. And XO200 is also planning to scale up to NEXO. So this is XO200. Again, this held about 150 kilograms in this vessel. We're scaling up to a 5,000 kilogram detector. That's about 1.3 meters. So it's still not big, right? 5 tons of xenon is not huge. And we're really taking advantage of this technology. So it's still a single phase liquid xenon time projection chamber. In this case, we will go deeper, so it looks like we will be sited in the Snow Lab cryo pit. And you can see that same sort of nested shielding model. So the detector's here in the center. There is a cryo fluid around it that helps basically maintain a large thermal mass so that we don't have to worry about our xenon heating up. It keeps everything nice and stable. It also provides shielding. We're inside a water tank. And then, of course, we're a mile underground at Snow Lab. And the sensitivity of NEXO will also reach that 10 to the 28 year goal in 10 years. And our discovery potential, which is important, we don't just want to rule this out, right? Like we actually want to measure something. Our discovery potential is very close to 10 to the 28 years, 0.74 times 10 to the 28 years. So what would it actually look like in NEXO? Again, it's not as simple as just looking at a single energy spectrum. If we were doing a more traditional analysis, what you would do is you would cut so that you had only things that look like your signal. So this is beta-beta-like based on our DNN. This is background-like on the bottom based on our DNN. And we would just get away from the edges of our detector. So we would make a really tight fiducial cut to reduce our backgrounds. And we would be looking here. We would zoom in on this part of the spectrum, and we would fit something to this, this energy where we expect our double beta decay peak, and we would tell everyone we discovered neutrinoless double beta decay, and everyone would look at us and go, "You're crazy. There is a gamma ray within 10 keV of your neutrinoless double beta decay peak. How could you possibly tell us that that's neutrinoless double beta decay when we know there's a gamma ray that lives right there?" And so that's why we can't do a traditional analysis. Nobody would believe it. The reason that people are going to believe us is because we're able to constrain the contribution from that gamma ray really well. So this is exactly why we need to do that simultaneous fit. If there's going to be a big component of that gamma ray here, it's going to be even bigger in this spectrum, right? We know that ratio really well, and that lets us constrain that background. Not only do we know that ratio really well in this fiducial volume, we know it in this larger detector where we have great statistics on our background. So that's the power, and it's actually more powerful than that because we're doing this multidimensional fit that lets us take everything into account at the same time. So this projection assumes that it doesn't make any assumptions about being able to find magical low background materials. We've made all the measurements of the material properties that went into this background model. And the thing to remember is, again, this is very dependent on the actual statistics. So when we make these projections, we actually have to, there's very wide bands, right? So we have our median half-life sensitivity here. We'll have a discovery sensitivity as a function of the half-life of neutrinos double beta decay, but we have a wide band there, right? So that's just something to keep in mind. What does that actually look like? I'll get to that in a second. So this is basically what I've already been describing to you. We have these three dimensions, the energy, the standoff distance, and the topology of our events handled by the DNN. And in any one of those, our signal to background, it looks okay, but it's not like amazing, right? It's really the combination of all three that becomes very powerful. So here's another way to visualize it. We take the three-dimensional space and we chop it up into bins based on signal to background, and then we just order them from worst signal to background to best signal to background. And we see there's actually a large part of that multidimensional parameter space where we have really high signal to background ratios. And that's why this is powerful. We just can't capture it in like a one-dimensional plot the way that the detectors with good energy resolution can. So here's just a little cartoon, because we're not just worried about right at our sensitivity potential. If we actually want to go farther with neutrinoless double beta decay, we want to have a lot of statistics, right? So our sensitivity limit is all the way out here at 10 to the 27 years. And let's just play that again. But as we go down to a place where we could actually make a, that's our 3 sigma discovery potential. If we go down to our 5 sigma discovery potential, we've got a lot more signal, right? And so basically, we're also working our way down in this half-life and working up in significance, also working up in the mean number of events that we're going to see. Now I have to zoom way out on my axes because I'm nowhere near where our current limits are. Our best limit in xenon is down here. This is the Kamlan-Zen limit. So I zoom way out on my axes and I keep playing my movie. So if neutrinoless double beta decay is just out of reach of Kamlan-Zen, when we turn on NISER, we're going to see a lot of statistics in the neutrinoless double beta decay peak, which is exciting. So there's a lot of room between that sort of nasty edge of our sensitivity and where we actually have discovery potential. There's a lot of space there. So I told you about 3 next generation experiments that have really comparable sensitivities. So this is taking Nexo, Legend 1000, and Cupid, and using a range of nuclear matrix elements, which is always tricky. These were chosen by experimentalists with the input of some nuclear theorists, but nuclear theorists all have their own opinions about this. And basically, for this particular range of nuclear matrix elements, we see really, really similar sensitivity to M beta beta and really, really similar discovery potential. The gray bar here is, of course, the inverted mass ordering that we were aiming for. We see that for the worst case nuclear matrix elements, none of the experiments completely cover it, unfortunately. So, we have to deal with that. Hopefully theory will improve and give us tighter bounds on this. All we can do is look for the half-life. But this is basically where we're looking at the next 10 years or so. We'll be looking for neutrinoless double beta decay to reach this sort of 10 millielectron volt reach. Any questions? So I will get to future experiments in a second, but I just want to remind you that there is a lot of available parameter space in the normal ordering as well, right? So the inverted ordering is interesting because we could get to the bottom of it. We can't get to the bottom of the normal ordering, but there's still a ton of phase space in the normal ordering here. So this actually doesn't matter which hierarchy we're in, right? This is still interesting to look at, and it's also interesting to test other kinds of lepton number violating physics, right? But thank you, yeah, good question. Okay, so now let's talk about the future. So let's assume that everything goes according to plan. We have a worldwide effort to run these 3 experiments. They all move ahead. And in the next 10 to 15 years, we'll have an answer. Either we see neutrinoless double beta decay. So let's assume we see it. What would we do? Well, if we see it soon, like if we see it very close to that place that's ruled out right now in the sort of 100 millielectron volt range, like what's just out of reach right now, we're going to see a decent amount of statistics, hundreds of events at least. It's not great, but it's not the worst. And in this case, we could consider building experiments to study the mechanism. And so what would we want to do in that case? Well, we'd want to observe it in multiple isotopes. That's going to help us disentangle the nuclear physics component. We might want to look at those angular correlations. We might want to consider going back to a gas detector so that we could look at that opening angle and rule out some mechanisms. And we have 2 options for that. A really big NAMO detector, where we have to figure out how to scale up that foil kind of configuration, get good energy resolution, or low pressure, or even a high pressure gas TPC has some sensitivity to that. So I'll talk about high pressure gas TPCs. And then in some cases, the mechanism could be further constrained by looking for that electron capture, double positron decay, electron capture beta plus, or double electron capture. So how likely is it that we can look for those? And then, of course, it's not just about double beta decay. If we see a big signal here, then we should be excited about looking for lepton number violation in complementary searches. So how realistic is it to look for something like double electron capture? Yes? I'm going to talk about it. Yeah, I'll talk about next. That's why I shouldn't have written low pressure here. I really am talking about high pressure. Okay, so how likely is it that we can see double electron capture? So we've actually seen 2 neutrino double electron capture. So I was telling you yesterday, like that side, it's harder to look for, like we kind of ignore it. But we actually have an observation of 2 neutrino double electron capture in xenon 124. And what happens here is we have our double electron capture proceed. The 2 neutrinos take away the Q value, and then we have basically a cascade of Auger electrons and X-rays to refill those orbitals. And that's the signal for 2 neutrino double electron capture. We know the total energy associated with that, and we know where to look for the peak. But it's an X-ray peak. It's not the Q value for this reaction. And so this was actually seen in the xenon 1-ton detector. This is from the xenon collaboration. There's 2 reasons that we haven't seen this in XO200. Anybody have any ideas? Our detector is enriched in xenon 136. Enrichment basically selects for the heavy mass stuff. There is no xenon 124 in XO200. Yeah, even if there was, if we had natural xenon in there, this is at sort of KeV, tens of keV scale, it's below our energy threshold. So dark matter detectors are great because they're great at low energy. They've got natural xenon, and so that's why xenon 110 was the first one to be able to see this decay. So here's the peak that they measured at the predicted value for this cascade. It has a 4.4 sigma significance, and they measure the half-life to be 1.8 times 10 to the 22 years. So again, extremely rare process. This is not what it would look like to look for neutrinoless double electron capture. In that case, you would see the Q value, and you would see it through internal Bremsstrahlung. So it would be at a different energy. than this. And then you would also see the cascade. So it's a very different search in a different region, but you know, it would be worth doing if we had a strong reason to look for it. And in fact, there's some papers that say, you know, this can actually be enhanced if you have if you have similar mass parent and daughter nuclei. So we could expect like a resonant process that might actually make it likely to look for that. So now let's talk about what we would do in terms of a gas detector. There is actually a Super NAMO demonstrator module, so scaling up from NAMO 3 to Super NAMO. It's not going to have a sensitivity that's sort of competitive with the ton scale experiments. It's only going to reach a sensitivity of 4 times 10 to the 24 years in selenium-82. But they are planning to scale up to 100 kilograms. Sorry, they're taking a demonstrator module with 6.3 kilograms. Not scaling up. The larger NAMO, if they built the full-size Super NAMO, that would be a goal of 100 kilograms of selenium-82. And they were supposed to have started taking data in late 2023. I'm going to assume that they did. So if they reach a 3-year exposure of about 17 kilogram years, this is the sensitivity they would get to. So the good thing is we're still working on this technology. So if we see a large signal neutrino double beta decay that says, yes, we should study the opening angle, we still have the expertise to build this kind of detector. We just have to make sure we can scale it up to a place where it's actually sensitive. Here's high pressure gas TBC. So this is next. And next is a little bit behind the other experiments in the sense that they haven't deployed a 100 kilogram scale demonstrator yet, but they are planning to, and they're going to be building that at the Confranc lab in Spain. And their projected 3-year sensitivity will be 5 times 10 to the 25 years, which is the same as the ultimate XO200 sensitivity. So they're working with high pressure gas. High pressure because you just want to get a lot of atoms in there. But being in gas phase, we actually have longer tracks of the electrons, and they have very good imaging. They also have less than 1% energy resolution. So and they believe they can get that down by another factor of 2 or more. So they have good energy resolution, better than in liquid phase. They also have the ability to do this tracking. And what we see here is as the betas slow down, they actually deposit more energy. So they call this the spaghetti and meatball signature, right? So you see 2 blobs at the end of your track, and that tells you that this was 2 betas and not 1 beta. And this is a very clear signature. This lets you throw away background really well. The only problem is it doesn't have great efficiency, right? They don't always see this. So this is a really nice signature, and they do have some sensitivity to the opening angle, even though being in a high pressure gas, you get a lot of collisions. So they're doing R&D on multiple prototypes, so they're really still working on what technology they would want to move forward with. But this is real data. So this is the difference between a single electron track where you only see 1 blob and a pair production track where you see 2 blobs. Right, so this is real, it's working. They've demonstrated it. And we'll have a 100 kilogram scale prototype detector for a larger next in the next few years. So this technology might also be a good path forward, moving to gas if we saw a big signal in the next generation of detectors. It would give us another handle. There's another cool thing that the xenon detectors can do that can help us knock down backgrounds. And that's barium tagging. So what's barium tagging? Well, when we undergo Neutrinoless double beta decay, we end up with an ionized barium-136 in our final state. And barium, especially singly ionized barium, is a really well-studied spectroscopic system. So rather than just relying on the event topology to tell you this looks kind of like double beta decay, you could be really sure if on an event-by-event basis, you could go in and confirm that the daughter of the decay you just observed was in fact barium-136, right? So Next has been working on this technology. They're using single molecule fluorescence imaging, SMFI, and basically what they're doing here is they have this fluorescent dye that is sensitive. It was developed for calcium, but it also works for barium. And basically when it receives that barium ion, in this case it's sensitive to the 2+ state, so that's even better, you don't have to do anything, it becomes fluorescent. And here's what that looks like. You get this peak in the surface that they're scanning over that's covered with this dye. And then a really common thing with fluorescence is if you keep looking at it with your laser, you keep exciting it, eventually it becomes bleach and it goes away. So that's what happened there, that was bleaching. But they're not the only ones working on barium tagging. Nexo also has a barium tagging effort. EXO was actually conceived because of the possibility of doing barium tagging. So we've been working for this on a long time, working on this for a long time. And the idea here is even in a liquid detector, if you knew where your event happened, you could go in, you could grab that barium, pull it out, do laser spectroscopy in ice. So we're talking about freezing xenon onto this cryoprobe, pulling it out, doing laser spectroscopy, and again, looking for a fluorescence signal in ice. And this has also been demonstrated. This is a Nature paper from a few years ago. This is what the emission spectrum looks like for xenon in ice. This group, Bill Fairbanks' group at Colorado State, actually had to develop this model for xenon fluorescence, or for barium fluorescence in ice. And they also have this single molecule sensitive, single atom sensitivity, single ion sensitivity. So you can see this. And they get it all the way down to less than 2.4 atoms. So you can see the signal is proportional to the number of atoms. Okay, so that's the fun aside about barium tagging. So that was our happy picture. We see neutrinos double beta decay with a large signal in the near future. But there's another possibility here that we only set a limit in the next generation. So we get to that 10 milli-electron-volt scale and we haven't seen anything. And then we really have to ask ourselves if we want to keep going toward the normal hierarchy. And there's a large number of people that really want to do that. And it's really tough. But we have to think about what could come next. You definitely need better than 1% energy resolution. So those liquid scintillator detectors are not going to cut it. You need something on the order of 10 tons, or in some cases, a lot more isotope. And so you really need one of these scalable technologies. And you need, again, heroic background rejection. So let me just tell you about large-scale xenon. So people are talking about doing this. You may have heard about ideas for DUNE even, dissolving xenon in one of the modules of DUNE. That's one idea that's out there for getting a large mass detector. You may have heard about Thea, which is a proposal for the 4th module of DUNE, which would either be a water Cherenkov or a liquid scintillator-based detector that could also have a dissolved double beta decay, either xenon or tellurium component and a double beta decay goal in addition to many other goals. But let's talk about a dedicated double beta decay experiment, just because this is what people are talking about right now. So here's this paper that discusses the ability to scale up for discovery at 10 to the 30 years. So now we're competing with proton decay, I guess. And they did this study for both liquid xenon and gas xenon. So our purple peak here is the Neutrinoless double beta decay signal in both of these cases. We can see in gas xenon we have a little bit better energy resolution, but we have worse self-shielding, so the backgrounds are a little bit worse. And yeah, so here's what it would actually look like. They've actually bothered to name it. So scaling up to a large-scale liquid xenon experiment would be called Origin X, observing rare interactions with the giant xenon experiment. And this would be scaling from something like Nexo, which is very human-sized, to something like 300 tons, and then to the kiloton scale. So people are thinking about it. There's a lot of technology that would need to be developed to be able to do this. And it is not you can't really ignore the difficulty of procuring xenon in these amounts. So just getting the xenon is hard in this case. But there's people working on it. They actually held a workshop last year to build consensus across the community of how we might move forward with the technology development needed for very large xenon-based neutrinoless double beta decay experiments of the future beyond the next set of experiments. So here's the outlook that includes origin X all the way out here. So there's our sensitivity. This is where the normal mass ordering sort of has that arm that goes out to low mass. So that's what this line is, even though we know the normal ordering goes all the way down. Origin X is able to really get into that. We also have a bunch of beyond ton scale proposed experiments that I didn't really talk about, but include things like the that module of opportunity at Dune proposal for tellurium and xenon. That would get lower than the next generation. So let me just walk through this real quick. Here's where we are now. The filled ones are completed experiments. And so we're at that 100 millielectron volt scale. We're going to push past that with some of the currently running experiments. So we've got some dark matter experiments with sensitivity like LZ. We have Quarry, which is still taking data. Kimwa and Zen is still taking data. And Legend 200 really just started taking data. Legend 200 is going to start cutting into that inverted hierarchy in a big way. And then the next generation upcoming detectors, Cupid, Legend 1000, Nexo, that's where we start to get beyond that inverted hierarchy, get down to this 10 millielectron volt target. And then some of these larger detectors, they get a little bit further, but they don't quite dig down here yet. And this is the problem with the mass scaling, right? We go like the mass scaling to the fourth root, right? So it's really hard to push down here. That's why we have to be talking about kiloton scale if we want to really get down to that limit. So that's why I say this is kind of wild. It's really, really hard. Doesn't mean people aren't thinking about it. So I'll just throw my summary up really quickly. Double beta decay is great to look for. It's we've got this window into beyond standard model physics, and Neutrinoless double beta decay is the most sensitive experimental probe of neutrinos Majorana mass. It's super complementary to other kind of searches. And ultimately, we can have tension with some of the neutrino mass measurements, and that would be interesting too. So there's a vibrant experimental program to search for neutrinoless double beta decay, and we also need theorists, nuclear and particle theorists. So hopefully it was interesting.
Thanks, Michelle. Can we have some questions?
Model dependent. In theory, the lifetimes of the double beta decay measured for various isotopes, they are still a bit model dependent because of the matrix element calculations.
So the half-life is what we extract from the data.
Yeah, half-life.
We measure the half-life.
Yeah.
There's no theory dependence on the half-life measurement. That comes directly from the experiment, and there's no prediction for it, right? It goes, there's phase space all the way down, so we don't know where it might be. So we measure the half-life, and that's always the half-life. You can then interpret that half-life in terms of a model. It might be like Majorana neutrino exchange where you have a particular nuclear matrix element, but we measure the half-life. That's not model dependent at all.
I was wondering, there are several models which predict those half-lives in theory, in practice. So Neutrinoless double beta decay is still not detected, but those are the same models that do the calculation for two neutrino double beta decays as well, I think.
Okay, so yeah, if you want to interpret it within a model.
Yeah, so can the data constrain on those models as well? The two neutrino data, can it constrain the model parameters?
Can the two neutrino data constrain?
Yeah, because we are still using plenty of models. We don't know which one is correct. So is it possible to constrain the parameters of the models using the data available?
I mean, two neutrino double beta decay is not going to tell you anything about neutrino mass. So it's
not about the neutrino mass, but the nuclear models which are included to
the nuclear matrix elements?
Yeah.
I mean, the same people will also have predictions for the two neutrino double beta decay matrix elements, but they're completely different. They have different propagators, different momentum transfer, and so really the two neutrino double beta decay half-life is not a good input to understanding the zero neutrino double beta decay nuclear matrix elements, unfortunately.
Okay.
There are other experimental inputs that the theorists like to compare to, things like muon capture. We also look at some nuclear reaction measurements that people have been doing at accelerators to support that effort. They're looking at like double charge exchange reactions. That can be an input. But ultimately, there's no other process that looks exactly like neutrinoless double beta decay. So we are beholden to theory at the end of the day if we want to interpret these half-lives.
Thank you.
Okay. I don't see any other hands raised, so let's thank Michelle again.